Hello again, everyone. So today we're going to be jumping back into talking about limits. Today we're going to be doing a little bit more about limit laws, and we're going to be applying limits a little bit more. So we're going to start off with a couple of basic rules. So first of all, we have the limit as x approaches a of just x. So this is not f of x, this isn't a function, this is just x itself. And you notice we have x approaching a, therefore, if x approaches a, the limit of x is just that a. So that's that limit law. You really won't see these two a whole lot, maybe this second one a little bit more than this first one. And this second one says the limit of c for any constant c as x approaches a is just going to be c. So if you consider c like, say, a straight line, then at any point on that line, it is going to be the constant value. So those are two pretty basic limit laws. Now we get to this monster. So this is kind of all of the limit laws summed up. Now you don't necessarily have to write down everything if you don't want to, but it is important to understand kind of how the idea of the limit function works. So f and g are just two functions, and what is important to note is the limit of f is L and the limit of g is M, and both are approaching A. So they both have to approach the same exact spot. So essentially, as long as you just understand that the limit can kind of be moved more or less wherever you want it to be, then you can do a little bit more when it comes to actually solving for limits. So for example, for the sum law, if you have the limit of two functions being added as x approaches a, it's the same thing as just essentially distributing the limit. So you're looking at the limit as x goes to a of f of x, and then adding it to the limit as x goes to a of g of x. So all of these are pretty important to understand. But again, you don't necessarily have to write down everything if you just look through them and you see that everything is just essentially being able to move the limit around. So when it comes to actual functions, it's a little bit more like distribution or factoring of limits, if you will. When it comes to something with a constant, the constant can be taken outside of the limit. So you're just taking the limit of the actual function like this. So if you're looking at the limit of like c times some function, you can just take the c where c is some constant out, and you have just limit of the function and multiply by c after. Same thing for multiplication, same thing of like just kind of distributing the limit and division. Now, if you have some sort of a power, you can bring the limit into the power without having to worry about um, any issues within the power. It's not a variable, so you're not trying to raise the limit to a power or anything. You're just applying it directly to the function. And then same exact thing with the root. So those are all just kind of intuitive. It does exactly what you'd think it would do. And once we actually get to some applications, you'll see that it's a lot easier than trying to look at all of this and understand what the heck is going on. So let's go ahead and try a question. Some of them are a little bit easier than others. You will see a little bit later on where the issues will come in. So the idea of a limit is if there's a point there, the limit is just the point. We saw that in the last video. If there's no point, then the limit is if both of the left-hand limit and the right-hand limit are going to the same exact side or the same exact location, then that is the limit. So what we want to do, first of all, is this says use limit laws. We can just go ahead and try to evaluate the limit in each of these. Now, I can break it up and say the limit as x approaches -3 of 4x plus limit as x approaches -3 of 2, but I know that this just means that I can plug in -3 for my entire function and see if it works. So I can say equals 4 times -3 plus 2. And you'll know immediately if there's a problem. The problem would be something like dividing by 0, right? But if you just get a whole number, then it's absolutely fine. So what you get is 4 times -3 is -12 plus 2, which is -10. So the limit as x approaches -3 of 4x plus 2 is -10 using the idea of the limit laws. So again, this is kind of a little bit more justification of like why you don't necessarily need to memorize all of the limit laws. It's a little bit more intuitive in the sense of you just plug it in and you hope it works. And if it doesn't work, we do have a way to work around that. All right, so here's a little theorem. Again, I think this theorem is pretty intuitive. You don't necessarily need to memorize this. So P and Q are polynomials, A is some number. Then if you have the limit as x approaches A of P over Q, then all you have to do is plug A into your polynomials. And that works because polynomials are continuous functions. So if you just look at a point in a polynomial, obviously the limit is just the point because there's nothing funky going on. There's nothing weird. It's just a continuous function. And this only occurs when the denominator is non-zero, of course. Otherwise, we do have an issue. So like I said, this feels a little bit more intuitive because a continuous function, at any given point on a continuous function, the limit is just the point. Oops. All right, so let's go ahead and just apply that real quick. So we have the limit as x approaches 3 of this polynomial rational function. So we will know once we plug it in if we have an issue. So let's try. So since this is approaching 3, we're going to go ahead and just try plugging 3 in. So this is 2 times 3 squared minus 3 times 3 plus 1 over 5 times 3 plus 4. Let's see here. 3 squared is 9 times 2 is 18 minus 9 plus 1 over 5 times 3 is 15 plus 4 is 19. 18 minus 9 is 9 plus 1 is 10 over 19. Since this is a real number, that is just the answer. We don't have any issues where we're dividing by 0 or anything like that. This is just the answer given that these are polynomials and this is a rational function. Now, we do get to the point where we may have some issues, and that issue would be something called indeterminate form. You may have heard of it before. This kind of defines indeterminate form as 0 over 0. I might go a little bit further and say that if you also have something like infinity over infinity or infinity over 0, or really like anything over 0, if you have any of these situations, you're going to want to follow these same exact steps. So if you can't solve your limit, use these steps. That's essentially what this is going to say. So what I'm going to do is I'm going to highlight what the key takeaways will be here. So it says first make sure that it falls under this, right? Okay, so obviously we're going to do that. We need to find a function that will satisfy the f of x over g of x, obviously. So what we're going to do is one of these three things. First of all, we're going to look at our function and we're going to see, is it a polynomial over a polynomial? If so, it's probably going to factor. If it factors, then we are going to go ahead and try to get factors for it, in which case the factors would cancel, and we try to go ahead and plug back in our limit. So the idea is that every single time we do something to our function, we want to go ahead and plug back in with the limit. And ideally, once we plug it back in, we will have gotten rid of the little problem area that we had, and it will solve. So if it's polynomials, we're going to factor and cancel out the terms. Now, if you see a square root, then we have a slightly different issue. So if you have any kind of a square root or even like a fourth root, any kind of a root, an even root specifically, we are going to use this idea of the conjugate. We're going to multiply by the conjugate. And I will give you a little refresher on what the conjugate is. But essentially, once you multiply by the conjugate, you will be able to cancel something out. And again, we will plug back in, and you're going to go ahead and see that we will get an answer. And lastly is if this is a complex fraction. So a complex fraction is something of the form some number over some number, but then there's another fraction on the bottom. So it's multiple fractions in a fraction. You just start by simplifying it, and ideally it should work out from there, but if not, you should be able to use one of these two techniques to solve right from there. And then lastly, just apply the limit law. So that's kind of what I was saying. So now I should define what a conjugate is. So a conjugate is using a root. The idea is you switch the sign in between the two terms. And so down here, I have a little note. The conjugate of an expression involving a square root is the expression with the sign in between the two terms changed. And here's a little example. If you have the square root of x plus 3, I want the sign in between the two terms to change. So if it's plus, it becomes minus. And it doesn't matter if your square root's first or your number's first or anything about it. It's a sign in between them that has to change. That is the conjugate. So you'll multiply by the conjugate, but when you multiply by the conjugate, you can't change it. So you're actually going to be multiplying, in this case, by something like the square root of x minus 3 over the square root of x minus 3, because this is just a fancy form of 1. We can never change our actual numbers. All we can do is manipulate the way they look. And in this case, this is just multiplying by 1, so we're not actually doing anything to it. All right, let's try some examples. First, we have this polynomial over a polynomial form. All right. Well, the numerator is pretty easy to factor because we see we have an x and we have no c term. So for the numerator, I'm going to factor out an x. When I take an x out of here, I'm left with x. When I take an x out of the minus 3x, I'm left with minus 3. Now, the key is typically, if anyone, including me, if I give you a question, there's going to be a term in the numerator that cancels out with the term in the denominator. So if you're taking a test or doing a homework and you're struggling to find a number in the denominator or vice versa that factors, look at the terms that you have in one of them, and most likely one of those two terms at least will cancel out with something. And ideally, the term that cancels will be the area where we have an issue. Well, I guess we should start by seeing that there's an issue. What I always check is just the denominator because honestly, it doesn't matter what happens in the numerator. So I'm going to say there's some number up here. All right, 2 times 3 squared minus 5 times 3 minus 3 is some number over, well, that's 9 times 2 is 18 minus 15 minus 3, which is in fact some number over 0, which we cannot have. So this is how we know right here that we have to do something further. We have to factor, we have to cancel, because we can't divide by 0. This is indeterminate form. In fact, this numerator will also go to 0. That doesn't necessarily matter quite as much, though. So here we factor the numerator, and we need to factor the denominator. It's a pretty surefire bet that the denominator is going to have this factor of x minus 3, because that's the problem. The problem is that we have 3 minus 3 in the denominator. That goes to 0. Everything just becomes 0. So typically, you could just start by doing that. Now, because this is 2x squared, your a value out front is not 1, it's a 2. You can use the regular methods of factoring if you know them. You could try the quadratic formula, or you can just kind of use this little trick. So let's see here. Here we have x minus 3. I know that I need this term right here. So to go from x to 2x, I know I need a 2x. To get a minus 3, the minus 3 needs to be multiplied by a plus 1, and we can check to make sure this works. So here's a little check. X times 2x is 2x squared. X times x is plus x. Minus 3 times 2x is minus 6x minus 3. And this is 2x squared minus 5x minus 3. And that is what we have here. So the way that I did that is I saw what term I needed to multiply my first term by to get the first term. And I saw what I needed to multiply this last term by to get the last term. And I confirmed that the middle term was in fact correct. All right. And this is the limit as x approaches 3. It's very important that we write the limit every single time. Well, now we have terms that cancel, so I can cancel those. We're left with the limit as x approaches 3 of x over 2x plus 1. Well, now that we've changed it, we can go ahead and try plugging back in our number. So this is 3 over 2 times 3 plus 1, which is 3 over 2 times 3 is 6 plus 1 is 7. Perfect. Well, that number isn't 0. That is, in fact, our limit. All right. Let's look at one with a conjugate now. All right, so I have a little note here that says for problems involving a conjugate, only distribute the terms that are conjugates. Leave the other terms in factored form for easier cancellation. And you'll see if you try to do it where you distribute everything, the only thing you're going to get is a mess. You're going to have to somehow refactor it, and it's just going to kind of leave you with a bigger issue. And I'll show you exactly what I mean. So again, the first thing we want to do is we want to try to plug in a number that the limit is approaching and see if it works. This is going to be some number over -1 plus 1, which is some number over 0, which does not work. So we know we need to use some other rule. We see that we have a square root, which immediately tells us that we need to use the conjugate. So I'll rewrite my original expression, the limit as x approaches -1 of the square root of x plus 2 minus 1 over x plus 1. And this is where I'm going to multiply by the conjugate. I'll choose a different color. I'm going to multiply by a fraction, and the fraction that I'm going to choose is based on the numerator here because that has the square root in it. So we're going to have a square root, keep everything in there, x plus 2, and we're going to have a 1. And the conjugate is changing the sign of the sign in between the two terms. So here we have a minus, it's going to change to a plus. And what we do to the top, we have to do to the bottom to keep it as the number 1. So we have the square root of x plus 2 plus 1. Because when you divide that, you get 1. Now, this little note tells us we want to distribute the terms that are conjugates, and we want to leave the other terms. And the reason why we do that is if we do it correctly, then whatever term we took the conjugate of will wind up being, once we multiply it out, one of the terms on the other part of the fraction that we leave. And we'll cancel that out, and our limit will work. All right, so let's go ahead and try. This is actually a difference of perfect squares. So if you know that little trick, we can use it, but I'll go ahead and write it out. X plus 2 times x plus 2 when they're both square roots. When you square a square root, it just turns into x plus 2. And I can show you if it's, let me erase this. If you have, this is a rule from pre-calc, if you have a square root squared, your square root and your square cancel out. And then we have this times positive 1, so plus the square root of x plus 2 minus the square root of x plus 2 minus 1 times 1 is minus 1. All over, and then since this is the term we didn't take the conjugate of, we're just going to leave it in the factored out form. X plus 1 times the square root of x plus 2 plus 1. And we notice here, square root of x plus 2 minus the square root of x plus 2 cancel out. And all we're left with is x plus 2, since the square root and the squared cancel out, minus 1. But 2 minus 1 is just 1. So we have x minus 1 over, oh, I apologize, that's x plus 1. Positive 2 minus 1 is positive. Okay, x plus 1 over x plus 1 times the square root of x plus 2 plus 1. And silly me, forgot to write the limit. X goes to minus 1. Like I said, that is very important to show us what we're doing. Now we see we have x plus 1 and x plus 1. We can cancel this, cancel this. And another important pre-calc thing that a lot of people just sometimes forget is if you cancel out everything in the numerator, you are left with a 1 in your numerator. So you have the limit as x approaches minus 1 of, you cancel that term out, so it's just the square root of x plus 2 plus 1. And when you plug in negative 1, oh, I meant to write a 2 there. I don't know what it is with this question. Plug in minus 1. 2 minus 1 is 1. So we get 1 over the square root of 2 minus 1 plus 1, which is 1 over, well, the square root of 1 is just 1. 1 plus 1 is 2. So your answer for this question is just a half, which is in fact the number, and it's not dividing by 0, so we're okay. All right, and now we see one with a complex fraction. So again, we'll try to plug in first. We know we're going to have some number in the numerator. The limit is as x goes to 1. 1 minus 1 is some number over 0, which we can't have. So we'll go ahead and try something else. Since it's a complex fraction, we're going to want to try to simplify this as much as possible, which in this case is going to be trying to simplify the numerator first. So this is a good refresher on working with fractions. What I'm going to do is I'm going to rewrite the numerator. I'm not going to write the limit right this second because I'm not looking at the entire function. I'm just going to rewrite the numerator. I want to rewrite this using only a single fraction for now. So what we want to do is we want to create a least common denominator. And what that means is we need both of our denominators to be the same. Well, since x plus 1 and 2 have nothing in common, in order to make the denominators the same, we need to multiply them by each other. So the 2 I need to multiply by x plus 1, but since I multiply it down there, I also need to multiply the numerator by that. And same thing over here. I need to multiply this denominator by 2, but I can't just change it. I need to also multiply the numerator by 2. When I do that, now I have a common denominator, so I can write it as 2x plus 1 like this, and I can combine across my numerators using the sign that we have here. So this is 2 times 1, which is 2, minus 1. So just x plus 1. And then we can simplify this a little bit further. So 2 minus x minus 1 over 2 times x plus 1. 2 minus 1 is just a positive 1, so we have minus x plus 1 over 2x plus 1. And that's our numerator. So I'm going to go ahead and plug that back into the numerator, except as this form, and I will rewrite the limit. So this is now the limit as x approaches 1 of minus x plus 1 over 2x plus 1 over x minus 1. And now I'm going to do a couple steps. So one step is I don't really love the minus outside this. I know somehow I need to cancel out this x minus 1. The x plus 1 won't do it. This will, but we need to adjust what's happening here. So I'll do that first. So we've got the limit as x approaches 1. I'm going to factor out a minus. So when I take the minus out of the x, it's just x. But when I factor a minus out of a positive 1, it's x minus 1. So now we see that we actually have something that we can cancel. I'll just rewrite everything for now. 2x plus 1 over x minus 1. All right, we still have a complex fraction. So what we need to do now is we need to make it into a single fraction. And this will be a little throwback, hopefully, to probably like 5th or 6th grade, with this idea of keep, change, flip, which tells us we want to keep the numerator the way that we had it. So we'll have the limit as x approaches 1 of, well, the numerator is the minus x minus 1 over 2x plus 1. We're going to change the division and multiplication, and we're going to flip the denominator. Now, it's important to note the denominator is just x minus 1. So you can write the denominator over 1. And that sometimes helps a little bit because now we have a fraction over a fraction, and that's a little bit easier to think about flipping, right? When you have something over 1, it's now just 1 over that thing, x minus 1. And then we can use our pre-calc rules that say if you have two fractions being multiplied, you just multiply across. So this is the limit as x approaches 1 of minus x minus 1. Well, times 1 is just itself, so I won't write that. Times 2 times x plus 1, x minus 1. Well, hey, look at that. Now we see we can finally cancel out the problem, which was the x minus 1. So this goes away and this goes away. And we're left with the limit as x approaches 1 of this minus still stays, and we'll keep a 1 because we canceled out all of the actual numbers here, over 2 times x plus 1. And we can try plugging it in, making sure it works. So we'll plug 1 in. Well, when we plug 1 into the numerator, nothing happens. Over 2 times 1 plus 1. So 1 plus 1 is 2. 2 times 2 is 4. So we get negative 1/4 as our answer here, which is in fact not dividing by 0 again. All right, and this is kind of the last idea. So sometimes limit laws don't apply. Sometimes it's a little bit weird. So the first thing we'll try to do again is plug in. Honestly, in this class, most of the time, it's not going to work. You might get one that works, but the idea is for you to know the rules and understand the concepts of how to solve them. So most of the time, you're not going to get one that just nicely works. So again, we'll try to plug it in. We get 1 over 0 plus 5 over 0 times 0 minus 5, which is both dividing by 0, so neither one of those works. Now, this doesn't necessarily satisfy any of the limit laws that we listed before. It doesn't satisfy the regular limit laws. You can't distribute that limit and do the limit of 1 over x, the limit of the 5 over x minus 5. It's not a complex fraction. There's no square roots. It's not the typical rational function that you would think of, but it is a rational function. So using that, we need to make this into a single rational function and see if that helps us. So again, I'm not going to write the limit because I'm going to just do some algebra on the thing that we have here, and then I will rewrite the limit after. So we have 1 over x plus 5 over x times x minus 5. So this, we just kind of identified the closest thing is going to be the rational function. So we're going to try to make it into the rational function that we want. So again, from before, we need to use this idea of the least common denominator. Here we have an x, here we have an x times x minus 5. So all we actually have to do is adjust this term here because we have an x in both of them. The only thing this guy is missing is an x minus 5. So I'm going to go ahead and multiply this by x minus 5. That means I have to multiply the numerator also by x minus 5. And then both of my denominators are the same. So I can put it over a single denominator. And I can combine my numerators. So x minus 5 times 1 is just x minus 5. Plus, again, so now once we have common denominators, we can go ahead and just use whatever operation is between them and either add or subtract across. So this is plus 5. But minus 5 plus 5, that's 0. We get x over x times x minus 5. But hey, look, x over x. The x's can go away. We're left with 1 over x minus 5. Okay, that's a pretty nice function now. We can go ahead and rewrite it as the limit as x goes to 0 of 1 over x minus 5. And we notice if we do plug this in, we do in fact get a real number. 1 over 0 minus 5 is negative 1 over 5, because this negative will be pulled out. We get a real number. We see that that's our answer. So we always essentially are just trying to do something to get somewhere. My advice to students is always just try something. If it doesn't work, try something else. If you don't know where to go, just start manipulating things a little bit. If it doesn't seem right, maybe it is, and it's just a really hard problem. And if this is an exam, if you do some form of work, I'll try my absolute hardest to give you as much credit as possible for doing something that is vaguely correct. All right. So this one is kind of a throwback almost to the last lecture. We are going to use the graph here, but we could also use a table to go ahead and actually solve what's happening. You know what? Let's go ahead and plug it in, and then we'll use the graph to verify. So we have the limit as x approaches 3 from the left. So a little reminder, when you have superscripts, that's telling you if we're coming from the left or from the right. That's not saying positive or negative. So we're looking at 3 from the left of the square root of x minus 3 and 3 from the right of the square root of x minus 3. And the reason why this is important is because this is not a continuous function. This is not a polynomial where everything is just the limits. This is definitely a truncated function, which means, as you can see, it stops somewhere. All right, so what we can do for A is we can go ahead and try plugging in a number that's a little bit to the left of 3, maybe 2.999. So we can say, all right, what about the limit as x approaches 3 from the left of the square root of 2.999 minus 3? Okay, well, the issue here is that this is negative square, the negative goes inside of the square root. When you do 2.999 minus 3, you get minus 0.001. But we can't have a minus inside of a square root. And so no matter how close you get from the left, you can have 100 nines, you'll have 100 zeros, and then a 1, you'll still have a minus. So you can't take a negative square root unless you want an imaginary number, which we don't. Therefore, this limit does not exist, which you can confirm using the graph. Coming from the left, there is no left. This is the starting point right here. It hits at 0. There is nothing down further. It's just starting there. So we've confirmed that this is correct. Now we can go ahead and try B. Algebraically, we can choose a number slightly greater. Let's go 3.001 maybe. So we'll say the square root of 3.001 minus 3, which is the square root of 0.001, which is a very, very tiny number, approximately 0, which we can again confirm from the graph. So we see coming from the right, we go down, it hits 0. So this is just a little trick. Sometimes your functions are uncontinuous, especially if it's a square root. And so you can do it algebraically, and then you can also confirm graphically if you know what it looks like using transformations or whatnot. All right, this is another example. So we have now a rational function where you might not know what it looks like. So a square root, some of you may know vaguely what a square root will look like. This, you probably don't know what it looks like off the top of your head. I know I don't. So since we're looking at the limit from the left, again, not a minus, it just means from the left, we need to use a slightly different technique here. Um, what we could try is we could see if there's any way of factoring it. Um, there's not anything that would help us. We could try plugging in 2. We know we have some number over 2 squared minus 2 times 2, but that's some number over 0, which doesn't work. If we try factoring this, we get x minus 3 over x times x minus 2. Nothing cancels there. So none of the typical ways that we would normally have to solve this actually work. So this doesn't work either. So since we're coming from the left specifically, what we can do is we can just plug in a number very, very close to it. So from the left, maybe we choose 1.999. So let's go x equals 1.999, and we'll plug it in. We get 1.999 minus 3 over 1.999 squared minus 2 times 1.999. And that is approximately 500. Now, when you see a number that big, you should start to recognize that that is probably going to indicate infinity. But because it's so big, I want to plug in another number to confirm. So let's say x is 1.9999. How about that? So if we plug in a bigger number, we go ahead and plug it in here, we get that this is approximately 5,000. And in fact, if you keep plugging in numbers going up, you'll keep getting numbers going up. And what you notice is that this number is just going to keep increasing forever and ever, which tells you that the limit as x approaches 2 from the left of x minus 3 over x squared minus 2x is positive infinity. So sometimes we do need to just kind of go back to the old ways that we know how to do, which is just plugging in numbers. It does become slightly harder if you don't use a calculator. But this is just kind of a surefire way of always being able to check what your answer will be. You can also know that this is going to be some sort of an infinity because at 2, as you can see from the factored form, this will be a vertical asymptote. And at vertical asymptotes, your function will either go to positive or negative infinity. So that's just like a little check that we know that this is either positive or negative infinity. All right, now we have this theorem. There will be a couple of bigger theorems that we use, and you can tell it's a bigger theorem because it has a name. So this is called the squeeze theorem. So let me highlight what's important. So given these functions, x is an a, we have this setup. One function less than or equal to another function, less than or equal to another function. And then we have this right here, where the limit as x goes to a of f of x is equal to some number L, which is also the limit as x goes to a of h of x. So that means that right here, the limit there will be L. Right here, the limit there will be L. And if we just use a little bit of basic reasoning, if you squeeze something in between two things that are the same exact thing, that means the thing in the middle has to be the same thing. So that's what this says right here. Then the limit as x goes to a of g of x has to be L. So this is a fun theorem to keep in mind. It's not something that we're necessarily going to use a whole lot, but it is something we're going to use a little bit. All right, let's go ahead and try an example. All right. Oh, I forgot. I had a little drawing. So this is just kind of an intuitive diagram. So this will help you understand a little bit more. So on the top is going to be your h function. On the bottom is going to be your f function. Obviously, if your limit right here, that's L, then obviously this function here, g of x, if f and h go to the same place, g also has to go to the same place. So this is just a nice little drawing to help you visualize exactly what it is that this theorem is saying. Okay, now we get to the example. So we're looking at some crazy looking function when we're doing the squeeze theorem typically, and this isn't going to be a function that we would normally be able to just take the limit of. This is the diagram that will go with it. We won't have the diagram given a question though. So this is just going to be kind of confirmation of like what it is that we're looking at. We're going to do it algebraically though. So we see the limit as x goes to 0 of x cosine of x. Again, we can try plugging right in. When you plug in 0, you multiply 0 by cosine, you get 0. but this isn't how we're going to want to do this one. So while that may work, you may get the answer just by plugging that in. We're going to use the squeeze theorem to verify this. So the idea of the squeeze theorem is you want to choose a function that is bounded. And what bounded means is that you have a lower bound that is a number and a higher bound that's a number. So when you write it in that interval form that we showed before, f of x less than or equal to g of x less than or equal to h of x, you have an f of x and an h of x that are numbers. And so given this function, the cosine is the bounded function. We know that cosine goes between -1 and 1. So cosine, as a little reminder, kind of starts up here and does this, where this is at 1 and this is -1. So what I'm going to do is I'm going to say, okay, I know that -1 is less than or equal to cosine of x, which is less than or equal to +1. All right. But what I need is I need x times cosine of x. So all I have to do actually is adjust my function by multiplying an x into everything. So now, as opposed to like with an equal sign where you have two sides, you multiply one on one side, one on the other. Now this is an inequality where we have three different things going on. So instead of multiplying only two things by it, we'll multiply all three. So if I want x cosine of x, then I need to put an x on all different parts of my inequality. So what we have is -x is less than or equal to x cosine of x, which is less than or equal to +x. So now once we've created our function right here to be exactly what we want, we can apply the limit to every single aspect of our inequality. So we have the limit as x approaches 0 of -x, and that takes care of that. And we want to see what this guy is too. This is the limit as x approaches 0 of x. Well, when you plug 0 in here, you just get 0. And when you plug 0 in here, you just get 0. Since the limit of the left is 0 and the limit of the right is 0, that tells us the limit as x approaches 0 of x cosine of x must also be 0, as is shown in the diagram. So because we're able to squeeze it between two different functions that we know -x and we know +x, which here, this guy is -x, this guy is +x, we can know exactly what's going on between those two functions. Now, this last example, we can't do exactly what we did, the original statement that I made. So I said we could plug in 0. When you multiply 0 through, you get 0. So we just know the answer. But we wanted to use the squeeze theorem just to kind of use it. For this last example that we have here, we can't do that. Because when you plug in 0 to x squared sine of 1 over x, this one is fine. But 1 over 0, that doesn't work. That is indeterminate form. So we do have to do something different here. This is where we absolutely have to use the squeeze theorem because we can't use any simple limit law rules. So we'll again use the squeeze theorem. So the squeeze theorem says we first want to find a bounded function. Well, sine is a bounded function. 1 over x doesn't really change anything about our function. Sine is a little refresher, starts in the middle, goes up, down, up like this, where the top is at 1 and the bottom is at -1. It's the same thing as cosine, has the same bounds. It's just shifted a little bit differently. So cosine starts at the top, sine starts kind of at the midline. So what that tells us is that -1 is less than or equal to the sine of 1 over x, which is less than or equal to 1. All right, that's good. But we're not looking for the sine of 1 over x. We're looking for x squared times the sine of 1 over x. Well, that's a really easy fix. So the squeeze theorem says that we can just kind of go ahead and create the function that we need and then see if that function is squeezed in between two functions we know. So I need x squared times the sine of 1 over x. So I will go ahead and multiply that in here. But what I do here, I need to do to all of the sides. So x squared here, x squared here. And I'll rewrite it. What this gives us is -x squared less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. Now that we have the function that we're looking for, we can go ahead and look at the limits of the left and the right. So the limit as x goes to 0 minus x squared. Well, here again, we can just plug in 0. Minus 0 squared is just 0. We can also look at the limit as x goes to 0 of +x squared, which is just the right-hand side here. When we do that, that's 0 squared, which is just 0. Since the left and the right are squeezed, in between, oh, well, since they're equal, then the middle term is squeezed in between 0, which means that the limit as x approaches 0 of this term here, what we're looking at, what we're looking to find, just has to be 0. So that's our answer. All right, so that's it for today. If you have any questions, let me know, and I will see you for our next video.